In the second half of chapter 25, we looked at our alkyl halides and the fact that, importantly, they can undergo substitution reactions. And this is one of the nicest bond-forming reactions that you're going to learn in this course. So whenever we do these reactions, we are looking for an alkyl halide, all right? So alkyl halide, such as bromine, which is what I'm going to use here, which is on a tetrahedral carbon. And it's usually secondary or primary alkyl halides that we're going to look at. So secondary, primary alkyl halides. These are the only ones that we're going to do the exchange reactions on. And then the next part is in a substitution reaction, we will be using a nucleophile. So I'm going to take a very simple example of our sodium hydroxide. And as we analyze this, what we have to do is we have to recognize what is the nucleophile part of this molecule. And in this case, it's the OH. Another way of looking at it, which is actually perhaps a little bit easier in the beginning, we'll do the mechanism just now, but what is easy in the beginning is possibly just to, when you're analyzing reagent, decide what is the nucleophile and is it a nucleophile or not, is if you see any sodium, potassium, or lithium. All right, so we're looking for Na+, K+, or Li+. If we ever see anything like that, get rid of it. Take it out of the picture, forget about it, and then have a look at everything that is left. In this case, we have an OH, which we know must be OH minus. And all we do is we just swap these two partners around, and that ends up being our substitution reaction. So we have an OH, and we've got the Br minus given off. Now, let's just think back. We did have the sodium present, so let's just throw that into the mix. We've got Na plus. As well in that. Okay, so there we go. The OH is switched, and there is our leaving group, which has gone. So we can do that for every single case of nucleophile that we can throw at you. So if I do another one here, I'm going to say KCN. This is quite a critical one. We look at this and we see, potassium, get rid of it. All right, all we've got left is the Cn, which we know is the nitrile anion, and it is negatively charged. So we can highlight that in the substitution reaction, the whole thing, whatever is left behind, don't throw anything away. The whole thing is going to do the exchange. And so we end up with Cn over there, and all right, now we've got the counter ion, so now we can remember, okay, we did have the potassium and the bromine has been given off. So we've got KBr being given off over there. All right, so that's the principle that you have to follow from. Now, if you follow that simple principle with these ones, seems nice and simple, but you need to be able to do that with other things. So take something which is a little bit harder, but actually it's not if you just follow these principles. Now we're going to use sodium methoxide, that's OCH3. Sodium methoxide. Methoxide is just the base form of methanol, just like hydroxide is the base form of water. So this is just the base form of methanol. What we do, we see the sodium, get rid of it, take it out of our minds, and we see everything else that is remaining. The OCH3 is the nucleophile. There's a negative charge on the oxygen. That's the part that's going to connect to the carbon. So our product is going to be, there's our carbon fragment, and then we've got the bond going to the O, and then everything else. We didn't get rid of anything. It's still OCH3. It's the whole bit over there. The only thing we get rid of is the counter ion. And then we can bring the counter ion back, and we've got NaBr again. Okay, so that should be fairly doable to you. But then now let's just take an example that doesn't have a counter ion on it. I'll take this one. It's just an amine. It's a primary amine. And what we do with this is we recognize that actually this is a nucleophile. Amines are brilliant nucleophiles. They're fantastic for substitution reactions. They're nucleophilic because of the lone pair of electrons. There's no negative charge. There's no potassium, sodium, potassium, or lithium. And so when we look at this, we recognize that of this molecule, the nucleophilic part is the lone pair of electrons on the nitrogen, but everything else is the nucleophile. It is the whole thing. We're not going to start ripping this molecule to bits and doing some other funny things with it. The whole thing is the nucleophile. It's the nitrogen which is the connecting part. So we draw out this molecule over here. Sorry, I'm running out of space a bit. So we draw that bit out there, and then we've got this new bond, not to bromine, but to the nitrogen. And the nitrogen is connected to all these different carbon atoms over there. I'm just drawing it back to front here, but it's 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. And the hydrogens have remained. Nothing has been removed from this. It's just this, as is. There's no potassium, sodium, or lithium over there. So we recognize, of course, now that the nitrogen must be positively charged. There is the whole nucleophile included in our substitution. And of course, what was remaining is the Br minus. Everything balances out now because we have the Br minus and the Na, the nitrogen plus over there. So that is fairly easy. All right, now for the mechanism. The mechanism of this substitution reaction is incredibly easy, but to show it to you, I'm going to just use another example looking at a nucleophile you haven't looked at before, but I want you to follow the exact same rules that we've done before. So we look at this molecule, we recognize that we have a leaving group that is an alkyl halide, that is a primary bromide. It's a very good leaving group. And now we look at this reagent, which we haven't seen before. Suddenly it's very confusing, but actually it's not confusing because all we have to do is recognize, wait, we've got a lithium over there. So the lithium we want to get rid of. And then once we get rid of that, what we see is a triple bond with a negative charge on it. And something with a negative charge is generally a good nucleophile. So we recognize that this whole thing over here, right, the whole thing over here is the nucleophile. So we can draw out the product without actually any more help, and we'll do the mechanism now. So this carbon is connected to the triple bond. So there goes the triple bond, and that. Now if you follow that out carefully, you see there is our nucleophile that we added onto the thing. So we did that correctly. Now, of course, we remember that we put the lithium bromide that was given off over there, so just keep that in mind. So this is the product, but the way this works is just one step, two arrows. All right, one step, two arrows that occur at the same time, and there's a flow of electrons from the nucleophile. All right, from this nucleophilic oxygen, the curly arrow is going to be donating, or the electrons are going to be donating their electrons to this carbon atom over there. Note, the arrow starts where the negative charge is. That is where the electrons are. Ends on the carbon that is going to accept those electrons. Right, this is our electrophile, the carbon that has the leaving group on. And then this carbon-bromine bond is going to break. The electrons are in the middle of this bond. The electrons are not on this carbon. They're not on the bromine. They are in the middle of this bond. So that's where they're going to start, the electrons, and they're going to end up on the bromine like that over there. And that's all that you need to know for the mechanism for a substitution reaction. All right.